problem 8, chapter 15 of Giancoli 6th edition. This problem is similar to one of the examples that we solved in class. So what we have is again an ideal gas and it expands. So first it's going to expand. I'm going to make a plot here so we can try to understand what is going on. PV, okay? So this is pressure and this is volume. So first it expands, it's at a certain pressure here and it expands, okay, and while this pressure is constant. Okay, so that's the drawing that I made there. After that, so they gave us what is this pressure, okay, I'll call it, yeah, they gave us this pressure, they gave us the initial volume, and they gave us the final volume for this process. After that, heat will then flow out of the gas, but at a constant volume. And this will happen so that the pressure and the temperature are allowed to drop. So the pressure is going down, the temperature is going down until the temperature reaches its original value. Okay, so the pressure is going down, the volume doesn't change until, and this process will happen until we reach the same temperature. So I'll call this point A, and the temperature here is equal to the temperature at this point that I'm calling B. Okay, so TA is equal to TB. So we have this whole process. Go from A to C and from C to B, and the temperature at the initial point and the final point are the same. So that's all they gave us, and now comes the question. First question is, what is the total work done by the gas? All right. First thing, there is work from A to C, right? Because I have expansion. But from C to B, there is no work, it's 0. So that's what I have to compute. The work from A to C is done at constant pressure. So it's easy to compute. I have to put that pressure that was given to us, the final volume, minus the initial volume. And that's it. That's the amount of work that is done by the gas. You just have to be careful with the units. The pressure they gave us in ATM. So change it to the international system. The volume they give us in milliliters. So remember to convert from liter to cubic meters, like this. Okay, and that's it. So then you're going to get the number for part A. In part B, what they say is calculate the total heat flow into the gas, into, out, whatever. So how are we going to solve this problem? First, well, what is important to know here is the total heat is for the whole process from A to B. And what we know is that in this whole process for A to B, there is no change in temperature. No, so they said that the temperature at point B and the temperature at point A is the same. So I know that the whole change in the internal energy from A all the way to B is just 0. And so I know that the whole change in internal energy in this process is 0, and I know that the whole change in internal energy is given by Q minus the work. So since the delta U is 0, I know that the whole heat is equal to the work done. So the value that we got for the work in part A is the amount of heat that flows into this gas. And that's the end of this problem.